Hello, I'm Jolin, and today I work on using genetic algorithm to help virtual creatures learn to climb the tricky mountain. This simulation is done in bipolate, where the creature evolve over time by trying different designs, mutating, and improving with each generation. Let's begin with part B1, which focuses on integrating the genetic algorithm with the mountain climbing task. For this task, I have implemented a system where each creature starts as a genome. This genome is then converted into a URDF structure that defines the creature physical model for simulation. Each URDF creature is loaded into the bipolate simulation using a p.load_URDF, then tested by running p.step simulation over many steps to evaluate how well it climbs. Next, I have implemented this fitness function under the evaluate fitness in the creature.py file. This fitness function rewards creature for climbing higher and getting close to the center, and penalize them if they make no progress. This score will guide the evolution. The genetic algorithm uses mutation, crossover, and structure changes like grow and shrink to involve better designs over generation. To test the different parameters, I have used a script called test_no_threads.py. It runs in a single thread. We help to keep the results consistent. Here we have the default parameters and the parameters I have tested. When testing each parameters, I only change one at a time, like the mutation rate or the population size, while keeping all the others constant. For the genetics algorithm, I varied the population size, mutation rate, and shrinks rate to see how each one affects the mountain climbing performance. For the genome, I tested different gene counts. Each setup runs for 100 generations, and I measured the best fitness, average fitness, and how many links the creatures are involved. All simulations are run for 2,400 steps, starting near the mountain base. So let's analyze the result, starting with population size. Population size controls how many creatures are in each generation. With a small population of 10, we see the lowest peak and mean fitness, which means the creature don't adapt well because there isn't enough genetic diversity. A middle population of 40 strikes a good balance, achieving the highest average fitness and steady improvement. A large population of 50 reaches the highest peak fitness but has a lower average fitness, suggesting that more diversity but less consistent progress overall. Next, we have the mutation rate results. Mutation rate affects how often random changes happen in the genome. A low rate like 0.1 leads to stable but slower evolution with limited new traits. At a moderate rate of 0.3, the fitness peaked higher and the population evolved more effectively by balancing exploration of new traits and stability. Higher mutation rates between 0.5 and 0.8 introduces too much randomness, disrupting the progress and lowering the fitness. Then we have the gene count result. Gene count controls the complexity of the creature design. One gene is too simple for effective climbing. 5 genes provide the best balance of complexity and involvability, leading to the highest fitness score. 10 genes create too much complexity, which makes involvement harder and reduce the performance. This slide presents a visual analysis of our experiments in a simulated environment. Each video corresponds to one of the key questions we are investigating. In the first video, we compare population size. Population 40 is larger and moves more actively than population 10, which explains its higher fitness. For mutation rate, the creature with a mutation rate of 0.1 barely move compared to those with a rate of 0.3, showing how mutation impacts the evolution. Finally, looking at gene count, creatures with 10 genes appear smaller and less active than those with 5 genes, likely due to the increased complexity, making evolution harder. Let's proceed to part B2, which covers the advanced portion of the coursework where we experiment with the encoding scheme. First, I experimented with involving the motor types to improve how the creature moves. Originally, the motors were fixed to just pulse and sine, but now I've added triangle and noise waveform to the mix. This involved changing the genetic algorithm to let motor waveform adapt alongside the creature shape. This allowed natural selection to find the best movement patterns for climbing. Now we have 4 motor waveform: sine, pulse, triangle, and noise, each producing different motion styles. This code here defines the motor class, assigning waveform based on control values and generating output signals for each motor type. This chart shows how the motor types change over generation. Initially, all 4 motor types are fairly evenly distributed, but a significant shift occurs around generation 40. As you can see that the noise motor increased dramatically and become the dominant type by the end, while sine motors steadily grow and support the effective movement. Meanwhile, triangle and pulse motors decline, suggesting they are less suited for the climbing task. This shift aligns with the observed fitness improvement, showing that noise and sine motors help the creature to climb better. In this video, we can see there are 2 creatures moving side by side. The creature on the left with involved motor types move more smoothly and naturally. The one on the right using fixed motor types has more rigid and less effective movement. This shows how involving the motor types improve the overall motion. I have also explored involving the individual physical shape traits like the link length, mass, and radius, while keeping other traits constant. This helped me understand how each trait affects movement and performance. This chart shows how involving the different physical shape traits impacts the climbing performance. Link length has the strongest impact with longer limbs, which provide a big advantage for moving across mountainous terrain. Link mass has a moderate impact, helping balance and stability in climbing. Lean radius has minimal effect and doesn't significantly influence climbing abilities. So when we compare the three traits visually, the creature with longer limbs moves the most, but looks wobbly and unstable. The one with larger mass looks bulky and moves moderately. The creature with a larger radius looks small and barely move. So to conclude, the optimal genetic algorithm parameters are a population size of 40, mutation rate of 0.3, shrink rate of 0.3, and a gene count of 5, which produce the most effective climbers. In evolution, it favors noise and sign motor types, leading to better fitness than fixed motors. Among physical traits, link length had the greatest impact on climbing, followed by mass, while radius had the minimal effect. Thank you.